Assume a small bar magnet is being suspended by a string in magnetic field. Now, bar magnet is suspended freely in uniform magnetic field, remains in equilibrium with axis parallel to the magnetic field. North is positive, so it gives out lines of force. South is negative, so it accepts it. So suppose a huge bar magnets N and S are placed over here. So there would be lines of force flowing in between two magnets. In this magnet is suspended by a string, a small bar magnet. Alright. Now when it is suspended, obviously it would align with its axis parallel to the lines of force, or rather to the direction of field. As we provided a small displacement and release it, we find that it keeps on oscillating. It keeps on oscillating. All right, it keeps on oscillating. Now let's try and understand this theta. This angular displacement that we gave was very small. All right, so as we release our our hand, we find that it starts oscillating. Now this oscillation, whether it is SHM or not, let's find out. All right, so what we did, a small angular displacement provided through angle theta and released, it performs angular oscillation. All right, fine. So it did so. Now this is the situation. Now this is the magnet. This is the axis of magnet. Now we know that the distance, the magnetic length is 2L, and this is north, which is positive. This is south, which is negative. And the pole strength we represented by small m or also by Q subscript m. Alright, so pole strength, these are the pole strength. And we have tilted the axis by angle theta. Alright, by angle theta. Alright, okay. And just for reference, I've also drawn a triangle that ways. Alright, this is N, P and S. Now we would understand the significance of this a bit later. Alright, so now let's come to derivation. Torque we know is force into perpendicular distance. So force we know is Qm into B, that is pole strength into magnetic field is the force here by which it is being pulled this side and pulled that side. Alright, so this is your towards positive side and towards negative side. Alright, so being pulled, so owing to which a torque is generated. Now force, we jot down the formula, and perpendicular distance is NP. This is the perpendicular distance. Alright, perpendicular distance between these two is this NP. So how do you find? Now since this angle is theta, so this angle also has to be theta. Now let's try and understand this triangle that I have made. Alright, now this line is parallel to lines of force. Alright, this line is parallel to lines of force. Now so this line and this line are parallel to each other. This is the transversal. So if this angle is theta, this angle also has to be theta, corresponding angles. Alright, so this angle is theta. Now if I intend to find sine theta of this, sine theta is what? Is opposite NP over hypotenuse. Opposite NP over hypotenuse. So we write sine theta is equal to NP over 2L. So NP, that's what is our requirement. NP is equal to 2L sine theta. That's what we substitute over here. That's what we substitute over here for perpendicular distance. NP is 2L sine theta. So it is QMB into 2L sine theta. Now what I did is I just placed this 2L beside QM. Why? Because QM into 2L is magnetic dipole moment. Alright, so this disappeared and gave a new form, that is capital M, which is magnetic dipole moment. So this becomes our formula now for torque, MB sine theta. Further, we had just deflected the magnet in equilibrium state by small angle theta. Now since this small angle theta, sine theta, since it's small angle, so we know that approximately for theta below 10 degree, sine theta can be approximately assumed to be theta. Alright, so that's what we did. So mb sine theta changed to mb theta. So first what happened is, first np, we got 2l sine theta as per triangle. Then with 2l we shifted towards pole strength, and pole strength into 2l is magnetic dipole moment, so it got the form of capital M. Now theta which is there is very small, below 10 degree, so sine theta gets converted to theta. So final formula is tau is equal to mb theta. Now tau is equal to minus mb theta. Why? Because it's tied by string, right? So when I am deflecting it this side, it will try to come towards the opposite. The more the deflection, with more intensity it would be coming back. Alright, so what we can say is, we have deflected the magnet lying in equilibrium by some angle in this direction. As we leave it, it will again try to come back into this direction. Now deflection was in this direction and restoring torque was in this direction, so two are opposite to each other, so minus sign. Alright, now another thing we know is, more the deflection, more the restoring torque. Alright, so two conditions, and also m and b are constant. Now so that's what it is. Now let's move ahead. Now tau, so m and b are constant, so here itself we have proved that it's simple harmonic motion. Now let's move further and try to again rearrange those things and try to find out again. Alright, so what happens? We know tau is equal to I alpha. I is moment of inertia, alpha is angular acceleration. So what happens is, IA is equal to minus mb theta. So what I do is I take I below this, so mbi. Now magnetic dipole moment, magnetic field and moment of inertia are all constants. So acceleration, angular acceleration is directly proportional to minus theta. So now instead of torque, we can also say in terms of acceleration, because in torque we had moment of inertia which was constant. So torque would vary with acceleration. So with acceleration also we can say the same thing. Acceleration and theta are in opposite direction. Theta was in this direction and acceleration for torque was in this direction. Alright, so it was vibrating this way, so it was moving this way, right? So these two are in opposite direction, so negative, and at the same time more the deflection, more the acceleration in reverse direction. So what we can say is, tau or angular acceleration is directly proportional to theta. Tau or angular acceleration are in opposite direction. That itself proves that this angular oscillation performed by this bar magnet is SHM. Alright, and obviously it has to be at small angle. Alright, furthermore, now alpha over theta or acceleration over displacement is angular acceleration per unit displacement. Alright, now we have formula 2 pi upon root of angular acceleration per unit angular displacement. That's what is the formula. So what we do is, for time period we write t is equal to 2 pi and alpha over theta. Alright, and alpha over theta already described it to be this. So in terms of magnitude we substitute over here and we get yet another formula For time period, in case of bar magnet, in case of small bar magnet performing SHM is 2 pi root of I over MB. Alright.